Hello everybody, and welcome to the virtual seminar series on Gaussian processes, spatiotemporal modeling, and decision-making systems. And thanks everybody for joining us. My name is Alex Turnen. I'm a postdoc at the University of Cambridge and one of the organizers that's going to be hosting today. I'd like to thank my fellow organizers, Z Wang, Lisa Simonova, and Jeff Pleiss for their work in helping put the series together. And I'm just going to start with a few brief organizational announcements. The first is that there's still a few speakers left for this term of the seminar. I think there's about 3 more. And so you can find the upcoming schedule on the website, which is gp-seminar-series.github.io. And you can join the seminars there by registering on Zoom with the link that's provided there. And you'll get an email with the Zoom link. Or if you don't want to register, you can always join us on YouTube, which is available to anyone. Seminars take place at 1600 UTC, which is Coordinated Universal Time. And just for purposes of this talk, if you want to ask a question during the talk and you're on the Zoom, then you can use the raise your hand feature or just type it into the chat. And one of the moderators or the speaker can kind of unmute you so that you can ask your question. With that said, it's my great pleasure today to introduce David Burt, who is a postdoc at MIT, who will give today's seminar. David, the floor is yours.
All right, so, okay, hopefully you can all see my screen now.
David, your video.
Sorry? Oh.
Perfect.
Okay, hopefully now you can see me as well as my screen. Thanks for the introduction, Alex. So today I'm going to be talking about modeling of ocean currents using physics-inspired kernels. So in particular, I'll talk about recent work using the Helmholtz decomposition together with Gaussian process regression to predict currents, as well as to identify upwellings and downwellings in the ocean based on sparse buoy observations. And this is work done with a team of people, including Renato, who's the first author on the project, as well as a bunch of other people kind of coming from a more statistics and machine learning side. And then we also have a few people on the team who are kind of more involved with ocean modeling, and some people who are actually kind of dropping buoys in the ocean and kind of collecting data and things like this.
Sorry, David, can I just ask you to try to make that full screen, because we have a bunch of sides of the screen that are not part of the presentation. You might click the...
This is in full screen on my computer, I think. I can zoom in. Is that a bit better?
Yes.
Okay, I think I'm losing a bit on the bottom.
Okay,
I think it's an aspect ratio issue. Sorry.
Can you try to press the green button in the corner?
Yeah, that's.
And can you try doing slideshow mode?
Oh, okay.
Okay, this is much better.
Okay, cool. Sorry about that. Okay. To kind of outline the task, oceanographers are interested in things like predicting the ocean current at a place. And the ocean current is important because it can impact weather. It can also impact transportation. If you think about ships moving across the ocean, they're affected by the current. And also things like dispersion of oil spills in the ocean. The other task we're interested in is identifying upwellings and downwellings in the ocean. So just to explain a little what that is. In general, we're going to have buoy observations. So we have buoys kind of floating along the surface of the ocean. And so we view the ocean basically from a 2D perspective, where we only see the surface. But we want to know where water is either coming up from lower layers or going down from the top layer to kind of deeper in the ocean. When it's coming up, we refer to it as an upwelling. And so if you were to look from kind of above, from these buoys, that would look like a bunch of arrows kind of going out from a region where the water is coming up. And so we'll also refer to that as a divergence. And then on the other hand, if the water is kind of going from a top layer down, if you were to look at the buoys, it would look like they were converging. So we'll also refer to that as a convergence. And in general, I'll refer to upwellings and downwellings kind of interchangeably as areas of divergence, with understanding that an area of convergence is an area of negative divergence. One reason we're interested in this is because since we get this kind of transfer from ocean water at the bottom to the top when we have an upwelling, or vice versa, these transfer nutrients between layers in the ocean, and so they can be important for things like fish harvests and transport of gases between layers in the ocean. As I kind of alluded to before, there are GPS tagged buoys which have been dropped in the ocean, and they look kind of like this image below. And they float around, and because they have GPS trackers, you can calculate the current based on their location over time. And so there are kind of many of these buoys floating around, and this is what we have for observations of the current.
Sorry, David, I'm going to briefly interrupt you to let you know that with the slides, there is the black box with the arrows at the bottom. I don't know if there's any way to get rid of that.
Yeah, let me. Oh no, that exits slide. I think that comes from having. Okay, is this?
Okay, let's just continue like this.
Okay,
this at least gets rid of the box. Sorry about this for everybody.
So even if we have thousands of buoys observed over months, we still don't get to observe the current everywhere. And okay, we're at a Gaussian process seminar series. So I guess a relatively natural question is, can we use Gaussian processes to make predictions, as well as to identify areas of divergence in the ocean based on these buoy observations? So we'd kind of like to know the current everywhere. We only get to observe it where we have buoys, and we'd like to make predictions based on those buoy observations. And what we find is that if you kind of naively apply Gaussian processes in kind of a straightforward way without taking into account some kind of physical information about the ocean system, and we see there's issues. For example, we see that like if you observe buoys moving in one direction in one place, in the same direction in kind of a nearby place, you might expect kind of a continuity of current. So a current to just continue between the buoys, and this isn't always exhibited well, kind of with the straightforward application. Also, the kind of straightforward application isn't very good at completing kind of eddies or vortices, so rotational flows within the ocean, and other kind of known physical properties of current. And I'll give some concrete examples later. So in our work, what we did was we placed a Gaussian process prior directly over the components of a Helmholtz decomposition to better incorporate physical knowledge of how fluids behave into ocean current modeling. Okay, so to give an outline of the rest of the talk, first I'll talk about kind of a straightforward application of Gaussian processes to buoy data, which I'll refer to as velocity GP throughout the talk. Next, I'll talk about some of the limitations we showed of velocity Gaussian process, both theoretical and some kind of more empirical things. Next, I'll introduce our method, the Helmholtz Gaussian process. I'll then discuss some of the benefits we're able to show of our method. And finally, I'll conclude by showing some experiments, both on real and simulated data, that compare the two methods in terms of both current prediction and identification of areas of divergence. So these upwellings and downwellings in the ocean. Okay. So throughout the talk, I'm going to assume that current is approximately constant in time. And so as a result, we can view it as a function from R2, so from latitude and longitudinal components to R2, so into a latitudinal velocity and a longitudinal velocity. This assumption that the current is constant in time is definitely wrong over long time scales. We're going to mostly restrict ourselves to looking at observations over a relatively short span of time where it's reasonable. And then I'll also talk briefly about how in future work we plan to build back in a temporal component. So kind of the most straightforward thing to do if you're at a Gaussian process seminar series and like to use Gaussian processes for spatial modeling is to place independent Gaussian process priors on the two components of the ocean current. So in this case, we've written that ocean current as F, and it takes a latitude and a longitude, and it gives you U and V, which are latitudinal velocity and longitudinal velocity, and we can place Gaussian process priors over these. We can then model the observed current as a noisy observation of this latent Gaussian process. And an approach very much like this was taken in a 2019 paper using stationary, in fact, I think isotropic kernels for Ku and Kv. So for kernels for these two components. They also considered time dependence in multiple length scales. So using additive kernels to try to learn kind of multi-scale behavior. We're going to focus on this really simple spatial model, kind of at one scale for modularity. And then I'll talk a bit at the very end about how we're working to build back up to kind of a more sophisticated spatiotemporal model. Okay, I'm now going to go into some of the limitations of modeling the ocean current in this way. So we're interested in behavior on the sub-meso scale, which is relatively small, so kind of on the order of 10 kilometers. And we know that rotational movements, like things like eddies, are known to make up most of a current, while upwellings and downwellings are kind of less common or have smaller magnitude over these scales. What we're able to show is that if you take the prior discussed on the previous slide, so if you model your the U and V component of the velocity field independently using isotropic kernels, then at any point in the ocean, if you calculate the variance of the rotational part of a field in the divergent part of a field, they actually have to be equal. So this is kind of implying that under a prior, we're forced to have the rotational and divergent parts of a field have the same magnitude, even though we sort of know this isn't really what the case kind of physically. So in particular, the velocity Gaussian process can't incorporate these kind of assumptions and prior knowledge we have about different magnitudes of rotations and divergent behaviors in the ocean. So another limitation is the velocity Gaussian process can't model any correlations between latitudinal and longitudinal velocities in the prior, but also in the posterior. And this is kind of true by definition in the prior, since we've chosen since we placed independent priors on U and V. But it's also true in the posterior because the likelihood model we've written down is isotropic, and so there's no way to correlate the U and V components when doing regression. So why might this be an issue? Well, if you imagine kind of a simplified ocean current, which is just a vortex spinning in a circle, you might expect the U component to be informative about the V component, because if you were to look at like when the U component is large in magnitude, the V component is small, and vice versa. And while we know the actual ocean current is more complicated than this, we still kind of expect that correlations might be useful to incorporate into the model. Okay, another property of this model, which seems kind of undesirable, is that it depends on reference frame. So in particular, if you take isotropic kernels and then you do something like maximum likelihood over kernel parameters separately, you end up with a model that depends on reference frame. So in particular, inference in the model is invariant to coordinate rotation if and only if the two kernels are equal. And so you can't expect that to be preserved if you do maximum likelihood separately over kernel parameters. So in particular, here's a little cartoon where we have red arrows, which you can imagine are buoy observations, and we rotate them by 45 degrees. In our predictions, these blue arrows won't necessarily rotate with them. And at least on kind of small scales, it seems plausible that we shouldn't be really sensitive to which coordinate frame we chose to do inference in. Okay, so now some more empirical things. We find that there's issues, and I kind of alluded to this on the first slide with the velocity Gaussian process in terms of some kind of simple modeling simplified ocean currents. So here we have this kind of vortex I showed before. The black arrows are the ocean currents at different points in space, and the red arrows are now simulated buoys. And so again, the arrow shows kind of the observed velocity field at the given point. And so we'd like to, based on these observations, be able to kind of predict the current throughout this vortex. But what we see when we apply the velocity GP is that we get a velocity field like this, which looks reasonable in the locations we have data. But as soon as we get away from the data, it doesn't really predict this kind of rotational behavior that's kind of the driving the vortex. Finally, we were interested both in prediction and identification of divergence. And we find that the velocity GP often struggles to identify or preclude areas of divergence based on sparse observations. So here we have a slightly more complicated simulated data set where we have the similar vortex to before on the top, and then we just have a straight current below. And you see we have kind of simulated buoys both in the vortex part and the straight current part. If you calculate the divergence of this field, you can see there's no upwellings or downwellings, and so it's 0. On the other hand, the velocity GP predicts both kind of a convergent area here shown in blue and a divergent area shown in pink. And if you calculate kind of the standard deviation of the predictions, these are kind of moderately significant. So it's around like one or a little over 1 standard deviation. So at least based on this data, you might think there were upwellings or downwellings here, even though we actually know, because the field is simulated, that there's no upwellings or downwellings. Okay, so now I'm gonna, I've mentioned the Helmholtz decomposition a few times. I've also mentioned divergence quite a bit, so I'm gonna now briefly go into kind of what these are. So as on the previous slides, we're gonna view the current as a function from R2 to R2. So we, again, have it as a function of latitude and longitude. We have a latitudinal velocity and a longitudinal velocity. So the divergence of a field is equal to the sum of the partial derivatives of the first component with respect to the first input and the second component with respect to the second input. So the formula is not too important, but kind of the picture to have in your head is that the simplest divergence you can have is kind of just these arrows which kind of go out from a region. And in this case, if you were to calculate the divergence using this formula, what you would see is that it's high in this middle region where the arrows are kind of growing, and then it kind of goes to 0 away from this center region. And so this, again, in the actual ocean, would correspond to an upwelling where water is coming up from below in this middle region. And so then when viewed from the top, it looks like the current is going out from kind of a point or region. So what the Helmholtz decomposition is it tells us that if we have a smooth enough function, and it goes from R2 to R2, then we can decompose our ocean flow into 2 terms, which I'll write as grad phi and rho psi. Phi and psi are functions from R2 to R. And the grad and rho rotational operators are defined in terms of mixed partial derivatives. The actual formulas aren't crucial for the rest of the talk. The thing to kind of focus on is we're taking partial derivatives and we're summing them. And we'll refer to the first term as the divergent velocity and the second term as the rotational velocity. And the reason for this is that if you were to take the divergence of a field and try to compute it, you would see that it's the sum of the divergences of these two terms. And in fact, the divergence of the second term is equal to 0. And that's just like you sum mixed partial derivatives and you take the derivative with respect to both arguments, and you can see one has a negative sign. So this term is just identically 0. So the first term, which we refer to as the divergent velocity, only determines the divergence of a field. And the second term determines the curl of a field. In the Helmholtz decomposition is also commonly used in 3 dimensions, but we're going to focus on kind of the 2-dimensional version. So visually what this looks like is you have your ocean flow, which in this case is not an actual ocean. This is just simulated. And you can decompose it into 2 fields. Here I've plotted in the middle the divergent field, and you can see there's kind of points where arrows come out. And then there's points where arrows go in, and these are divergent and convergent areas. And then the rotational field, which kind of as the name suggests, looks like a bunch of areas where you have rotation, but you don't have any of these upwellings or downwellings. Okay. So now we've talked about the Helmholtz decomposition. I think it's there's kind of a straightforward thing to do, which is to place priors over the potentials of the Helmholtz decomposition. So it's phi and the psi. Remember, these are both functions from R2 to R. So we can just place kind of standard univariate Gaussian process priors independently over these 2 components, and then define kind of this latent current field as the sum of the grad operator applied to phi and the rotational operator applied to psi. And then use the same likelihood as before. And because the 2, if we place Gaussian process priors over these phi and psi, and because we're just applying linear operators to them, and Gaussian processes are kind of, Gaussianity is preserved under linear operations, we get that this latent function f is also a Gaussian process, and we can compute its covariance kernel. And again, the exact formula isn't crucial, but it's computed in terms of mixed partial derivatives of the kind of base kernels that we use. And so we can compute these just with automatic differentiation. And well, the exact formula isn't crucial. One thing to just note is if you have k phi equals k psi, then these off-diagonal terms end up being 0. And you actually get an instance of the Gaussian of the velocity GP, but with derivative kernels, with kernels which are derivative. So this case maybe isn't so interesting. But otherwise, we end up with correlations between the U and V components, which we didn't have in the velocity Gaussian process. So otherwise, it is actually a distinct model. So in practice, what we do is we parameterize k phi and k psi separately, and then we select parameters via maximum marginal likelihood. Okay, so we're definitely not the first to take inspiration from physics for doing kernel ridge regression or Gaussian process inference or other kind of related problems. Most of the past work emphasizes the use of kind of physics-inspired kernels to place kind of physical constraints on the problem. So things like, the field that you're interpolating is curl-free or divergence-free, and you want to gain some efficiency by incorporating this into your model. And so one thing that we show is that even in the absence of these known physical constraints, the inductive biases provided by parameterizing our model in terms of a Helmholtz decomposition can be useful. And especially if we use maximum marginal likelihood to kind of select parameters differently. So just to kind of talk about some of the earlier work in this direction, there was earlier work by Narkowicz and Ward introducing kind of curl-free and divergence-free kernels, or kind of more generally kernels satisfying these kind of linear constraints on the outputs, in order to build physical constraints into kind of interpolation with kernels. That was followed up by work in 2010 by Machado and Castro, looking at kernel ridge regression and investigating kind of identifying curl and divergence-free fields. They also considered some linear combinations of two, which starts to look pretty similar to what we're doing. But they don't really figure out how to balance, or don't really investigate how to balance kind of the trade-off between the curl and divergence-free components in the Helmholtz decomposition, which is kind of one of the main focuses of our work. Maybe the most related paper was a 2013 paper by Wallstrom et al., considering Gaussian process regression for electromagnetic fields. And because of properties of electromagnetic fields, they know that the divergence and curl-free components are actually equal in some points in space, in particular at the observed data points. And then they have observations of the curl-free components. So they use pretty similar kernels to us, or basically the same, but they have quite a different likelihood. And they also parameterize the kernels to kind of have the same parameters. And that's makes a lot of sense in the model they have, since they know the fields are equal at certain points. But in our case, if we were to take a similar approach, we wouldn't really gain that much from using the Helmholtz parameterization, since in that case, it would just be an instance of the velocity GP, since as we talked about kind of on the previous slide, that amounts to modeling U and V independently with our likelihood model. I'm now going to talk about kind of some of the properties of the Helmholtz GP. And so these will be kind of contrasting against the earlier properties I discussed of the velocity GP. So the first is that the divergence and rotational components of a Helmholtz GP can have different prior variances as well as length scales. And this basically comes because we parameterize them differently. And so what that looks like in practice is, here I have a field which I've simulated by sampling from the Helmholtz GP prior. And in this case, I've made the magnitude of the divergent component quite small. And so you can see that grad phi is quite small. So the field is primarily rotational. On the other hand, if you make the rotational part of a field small and the divergent part large, you get a very different looking sample from the prior. So the model can kind of model a wide range of different ocean properties by kind of changing these parameters. And so in practice, we're going to set the length scale and magnitudes separately via maximum marginal likelihood. So we can hope to learn kind of if the field is mostly rotational or mostly kind of divergent. Okay, so here we have this vortex example from before, where again, the current is simulated and is shown by the black arrows, and we just have observations from the red arrows. To remind you, when we use the velocity GP, we got this predictions where the prediction looked pretty reasonable near where we had data, but the model didn't extrapolate well to complete the other side of the vortex. And now using the Helmholtz GP, we see we get kind of much better ability to complete vortices. So the Helmholtz GP is able to kind of recognize that the field is rotational and extrapolate a bit better, kind of in distances not too far from the buoys. The other thing we're interested in, as well as predicting currents, is identifying divergences. So here we have, again, this slightly more complicated simulation where we have this vortex on the top and a straight current on the bottom, which, as we discussed previously, has a zero divergence if we calculate the divergence of a field. And if we look at the velocity GP, we saw this previously. It kind of predicted this convergent area in blue, as well as divergent areas in pink. And now if we look at the Helmholtz GP, our predicted mean is very close to zero everywhere. So the model correctly recognizes that the flow is divergence free. Finally, the Helmholtz GP is even if we parameterize these two kernels separately, is rotationally equivariant in the sense that if we were to first rotate our training data, as well as the points we'll predict at, then make our prediction and then rotate back, we would get the same prediction as if we just trained on the original data. And so here's kind of that cartoon of the of what would happen. So we again have these red arrows, which are our training data. And if we rotate it by 45 degrees, we'll get the exact same, we'll make the exact same inferences as we would have had we first rotated the data. Okay. Now I'm going to talk through a couple more examples, both on simulated and real data. First, looking at a Duffing oscillator with two areas of divergence added, or an area of convergence and an area of divergence. So here we have the current is represented by these black arrows. The red arrows, which are scaled up some just for visibility, are these are the observed buoys, which are simulated moving around in this field. And so we should expect there to be a divergent area here. You can see kind of the arrows are pointing out from this point. And then a convergent area here, which would correspond to a downwelling. This would be an upwelling. And we're going to be interested in whether the models are able to identify these and then also predict kind of low divergence everywhere else, since the field is purely rotational. We're going to focus actually on prediction. So what we expect is the current to be continuous through here, which we see is true of the actual field because we have data here and here pointing in the same direction. And so we see that the velocity GP kind of fails to extrapolate to this region. And that's maybe not so surprising if you're not so surprising because the kernels are stationary and this region is kind of far away from the data relative to the length scales of the kernel. And so the model reverts to the prior here. And similar things happen here where we expect kind of to see, again, kind of current flowing in the opposite direction. On the other hand, the Helmholtz GP is kind of better able to model this continuity of current, which was again one of these desirable physical properties that we found the Helmholtz, the velocity GP kind of missed out on. Okay, the other task we're interested in is identifying divergences. And now we're going to switch to talking about kind of real data. So these are actual observations of buoys. And we'll start with a pretty large number of buoy observations. And what we should see is here you can see kind of the arrows are coming together. And so we expect there to be an area of convergence here. And the velocity GP identifies this area of convergence as well as these two areas of divergence around it. Helmholtz GP kind of makes very similar predictions. with this data. We don't have access to ground truth. So this is kind of the closest to ground truth we have, is that these two models roughly agree on the large data. We then consider a downsampled version of the same problem. So we have fewer observations over the same region. And what we see is that the Helmholtz GP is still able to identify this convergent front, but the velocity GP kind of predicts no divergence kind of in the region. So we don't see really any area of convergence here or areas of divergence from before. And the Helmholtz GP looks fairly similar, although maybe not as quite as good as when we trained on the larger data set. So the Helmholtz GP generally seems to be able to identify these upwellings and downwellings with more limited data than the velocity GP. So just to give some sense of kind of how the methods perform across a range of tasks, we looked at a bunch of simulated experiments. So the vortex was straight current, which I've shown on previous slides. We also just looked at some areas where we just had kind of a simple divergence. We also looked at these kind of Duffing oscillators with then areas of divergence inserted. And what we saw was that kind of on most of the tasks, the Helmholtz GP was much better able to recover the divergence field. So the table is showing kind of the RMSE. Again, we have access to ground truth divergence because we've simulated the field, and so we can just differentiate to calculate these divergences. And so we just calculate the RMSE on kind of a dense grid. And what we see is the Helmholtz GP is better on most of the tasks, but not all. We also considered another baseline, which was a neural net-based approach. So dissipative Hamiltonian neural nets, where kind of they just try to directly learn the divergent and rotational components by neural nets. And this method really struggled on the tasks that we saw, that we tried. We were usually trying with very few observations, so it could be that the neural nets just didn't have kind of enough data to kind of learn from. So just kind of to give an overall summary, we demonstrated that placing Gaussian process priors over Helmholtz decomposition allows us to better predict ocean currents, as well as identify areas of divergence relative to kind of a more straightforward approach to GP inference in this problem. And I should say it's slightly more computationally expensive, but not like orders of magnitude. It's about 4 times more expensive. So it's pretty practical still to run on medium-sized problems without any real issue. We have a preprint up called Gaussian Processes at the Helmholtz, a more fluid model for ocean currents. We're also still kind of working to build back in important parts of the model to kind of better reflect properties we know in ocean fields. So what I was discussing today was just a spatial model, and we'd like to make it back into a spatiotemporal model. It's not 100% obvious what the best way to do this is. In particular, do we need to account for things like periodicity in the temporal dimension, and if so, over what scales? Also, is it reasonable to assume that currents at the same spatial location completely decorrelate over time and do something like a product kernel? Or is there some additive part that we need to take into account, or some more complicated interaction between space and time we need to account for? Another kind of interesting point I didn't get into is currently we basically need to either downsample the observations or smooth them in time. Because there's some buffeting from wind, which creates waves, and so you end up with kind of some correlated movement, like spatially and temporally correlated movement over similar scales to what we're interested in modeling current as, but we're not really interested in this effect of a wind. So it would be nice to build this phenomena into some sort of correlated likelihood model to avoid having to do this downsampling and smoothing, instead of kind of build this process kind of more directly into our model of the system. So thanks for listening to the talk, and I'm very happy to take any questions now.
So I wanted to say thank you very much, David, for the wonderful talk. Just a reminder for anybody who's interested in asking questions, you can type these into the chat in the Zoom, or you can raise your hand using the Zoom option, and then we'll unmute you so you can sort of ask questions. And just to add a second point, we're also, following the usual way that we organize the seminars. We will first have a period of questions that are recorded and live streamed on YouTube, and then at some point we will transition to questions that are not recorded for anybody who's maybe doesn't want their question recorded. I guess if nobody has questions, I actually have a question, which is, in models like this, I'm curious, so effectively we're trying to model fluid flow using this buoy data in order to better understand where ocean current are. Like what's happening with the ocean currents. I'm curious if there's any other features, because when we think of GPs, at least I think of in some cases like a spatial kind of interpolation type model, and I'm curious whether there's additional features that one could incorporate here. So in this particular task, or whether it's just like a pure interpolation type problem.
Yeah, so we haven't thought much about this. I think one thing that does come to mind is this kind of final point I made related to wind. I'm not sure how much observations there are, how many observations there are of the winds in these regions, but probably if we had a model of the wind, that could be useful in kind of modeling kind of this local effects. Beyond that, I'm not so sure. Yeah, that's just one thing that kind of jumps to mind as potentially useful. I guess maybe other like weather variables could be useful, but we haven't really looked at this or thought about this. Okay. So yeah, it's primarily an interpolation task at the moment.
If there was other features that one would incorporate into the model, then like, do you have any ideas technically about like how to actually achieve that?
Yeah, I think it's not totally obvious to me what you're after with that. Like, in the sense like I feel like it depends a lot on how you think the feature like relates to your ocean current, right? So, or to the movement of buoys, right? Because the wind isn't necessarily affecting the ocean current per se, although it might be, but it definitely is affecting kind of the buoys themselves can be buffeted by it. For other variables, I'm less sure, but I'm also definitely not an expert on ocean, so I feel like I would want to ask some of the people who are and are involved with the project, kind of like what's physically plausible there. Yeah.
Cool. I appreciate the thoughts. Thank you so much. I guess at this point, we will move to conclude, in the absence of any other questions, we will move to conclude the live stream. And so I wanted to just again thank our audience on YouTube for joining us today, and remind that we will have another seminar. I think the next one is in 2 weeks, if I'm not mistaken. And this is listed on our website, which is gp-seminar-series.github.io. So check it out. And thank you again for joining.